Hello, we are Group 9. Today we'll present our project on designing and implementing an integrated production and inventory management system tailored for manufacturing and supply chain operations. We have 6 main parts here, as you can see on the slide. The first one is introduction, database design and implementation, advanced database objects, database security and administration, Python application development, and the last part is conclusion. About the project overview and objectives. This system aims to streamline the entire production workflow from managing production orders, tracking materials and components, and updating stock automatically upon order completion. The key objectives of this project is to improve data accuracy, enhance real-time visibility of production status, and enable timely reporting and alerts for better decision-making. The ultimate goal here is to reduce inefficiencies, optimize resource allocation, and ensure smooth flow of materials from suppliers to delivery. The second part, we're going to talk about the database design and implementation. So this is our ER diagram. This ER diagram contains 9 entities: products, materials, BOM, which is bill of materials, material supplier, suppliers, and supplier daily. Next one is orders, plans, and categories. As you can see, one product can appear in many orders, while each order contains exactly one product, but there may exist one product may not appear in any orders. About the relationship between products and categories, each product belongs to one category, and each category can include multiple products. There's a many-to-many relationship between products and materials via BOM, which is bill of material, since products may require multiple materials, and each material may be used in multiple products. Similarly, there's a many-to-many relationship between suppliers and materials via material supplier here, which is a associative entities. Because materials can be supplied by many suppliers, and one supplier can also supply multiple materials. The relationship between material supplier and supplier daily is that one supplier can have many supplier daily records, and each supplier daily records has one supplier. Let's move on to the relationship between orders and plants. So each order is manufactured at one plant only, but each plant can process many orders. About the relationship between orders and categories. Each order can only produce one category, but one category can be in many orders. The next one is about the relationship between plants and categories. In our system, only one plant can produce one category, and each category can be only produced in one plant. These relationships are managed through the use of foreign keys in junction tables. After having the ERD, we have a relational schema. You can see the relationships between tables and the primary key with foreign key in each table.
Now we will move to database security and administration. Firstly, we will create roles for production manager, warehouse staff, and finance staff. The first step of the process is creating user. We will use the create user statement to create user, production manager, warehouse staff, and finance staff, and identify by the password for each user. Next, about user roles, we will use the grant statement. The production manager will hold full privilege over all database objects and operation. Because the user oversees the entire production process, they require unrestricted access to manage materials, update production data, monitor warehouse inventory, and handle supplier and other information. The warehouse staff can select, insert, and update on materials, material supplier, products, suppliers, and supply delivery tables. This privilege allows staff to manage inventory records, update material receipts, and track supplier deliveries. And this staff can select only on BOM, categories, orders, and plans table to retrieve reference information without altering sensitive production or planning data. The finance staff can select, insert, and update on material supplier, products and supplier daily tables to support cost tracking, financial reporting, and budget management. This tab can select only on BOM categories, materials, orders, plans, and suppliers table to reference production-related data when needed. When privileges are granted, we will use the plus privilege to ensure change apply consistently. Next, we have to protect sensitive supplier and pricing data through permissions and encryption. I did talk about protect sensitive data through permissions, so now we will talk about encryption. Let's talk about the data fields that need to be secure first. We have unit cost from material supplier table and supplier name, address, and phone number from supplier table, and unit cost, total price, and status of supplier daily table. And to encrypt these sensitive data fields, we use the AES encrypt statement with a key. We have an example here. This script is encrypting unit cost data fields in material supplier table. And I set up the key is my secret key last pick. After encrypt the data, if users want to view them, they will use the AES decrypt statement with the key we use when encrypting. The script will look like this picture if user want to select from material supplier table. After running this script, you can see the unit cost column, which were hidden before. The last part of database security and administration is develop backup and recovery plans. Let's talk about develop backup task first. The first step we need to do is creating backup script file in Notepad. We will use a script like this picture, and let me explain this script. The first row is the folder containing the MySQL time file on the computer, and the second row is the folder where the user wants to save the backup file. And next, it is a database name and the date when the backup was created. And after the P, it is the password of user. And then you can see the script file in the folder that you want to save the backup file. After that, you need to run this script on CMD command line, and this app will look like this. When it's done, you will see the backup file will appear in the folder that you requested earlier. About second task, recovery plans. We will use the task scheduler app on Windows, and I will explain how to make a recovery plans on the app. First, we will open this app and click create basic task on the right of screen, and you will see a window will appear. Now you will name the task and choose the time that you want to start, and select start date and time that you want to run backup. And in action, you will click to start a program and click browse to choose backup script file that you made earlier, and click finish. After that, if you want to see the new task that you just made, click the task scheduler library and you will see it.
Now I introduce the advanced database objects we implemented: views, triggers, user-defined functions, index and optimization. Demonstrate how each works through live queries. The first part is about view. We created a view to track current production status that combines data from the orders, products, plans, tables using joins. It displays order details and uses a case statement to show if each order is on schedule or delay, depending on the expected end date. So to demonstrate this view in action, we run a query to list all current production orders along with their delay status. As you can see, we have 4 order ID is in delayed. So this instantly gives managers a clear real-time picture of ongoing production and highlights any orders that are at risk of running late, so interventions can be made promptly. The next view, we create a material usage in progress view. So we also use join between orders, products, bills of material, which is BOM here, and materials to calculate the total quantity of each raw material needed for all active production orders. This multiplies the required quantity of each material per product unit by the order quantity, giving procurement teams precise data for planning material purchases. So to demonstrate, we query this view and immediately see a detailed breakdown of all materials needed for in-progress orders. As you can see, the total material usage for each order here. So this makes material planning more efficient and proactive. The next view, we want to track the supplier deliveries. So this view links supplier delivery with suppliers and materials using joins and calculates the number of day left until the expected delivery date. Managers can easily filter for deliveries due within a certain time frame, such as those arriving in 3 days or less. When we run a query on this view, it quickly highlights urgent deliveries, helping the team prioritize follow-ups and avoid supply delays. As you can see here, we have the column days left for each delivery ID. So this real-time information supports smoother production by ensuring that materials arrive on time. The next part, we're going to talk about trigger to automatically update product stock after production completion. To ensure inventory is always accurate, we create a trigger that runs after any update to the orders table. First, we create a logs table to keep an audit trail of stock changes. After that, we create a trigger by declare old quantity with new quantity. Whenever an order status is changed to done, it retrieves the product current stock quantity, adds the finished quantity to it. It logs both the old and new stock amounts with a timestamp. So to demonstrate the trigger, we update an order status to done. So we have the order ID 00196 here, but I already updated. So let's see this query from the log to see whether it updates or not. As you can see, after update the order ID to done, the products from the old quantity, it is added the new quantity. By querying the logs table, we can verify that every stock update is tracked in real time, ensuring transparency and accurate inventory management. So the next advanced database objects that we want to talk about is user-defined function to calculate material cost per product unit. We implemented a user-defined function that sums up the material cost needed to produce 1 unit of a product. It uses information from the bills of material, BOM, and supplier prices from material supplier. To demonstrate, we call this function for a specific product, and the query returns the total material cost per unit. As you can see in the table, we have the product ID P001 with phone table, and its material cost per unit is $118.
Okay, so let's move on to the topic of index optimization and how it's improved database performance. Next, we'll try to optimize the queries by applying appropriate index strategy to each case. In the first case, we optimize a simple query by creating a single column index on the status field. So now, to check the query plane before and after using the index, we will run the explain and explain analyze on MySQL. First, I will run the explain query before adding any index. As you can see, the type here is all, which means that MySQL had to perform a full table scan. Next, I will create an index on the status column. I will run the explain query again. Now the type is changing to ref with the key order status we've just created earlier on. This means now that the query only using the index, and it will only examine the relevant rows. Now we can compare the two query planes. The query plane before adding the index showing that the cost is roughly 20. After adding the index, the cost is lower, just above 1. And also it's had only one step, which is the index lookup. So probably this query is running faster. In the second case, we'll create the composite index on product ID and the status column. This type of index is useful when query filters on multiple columns. And to check the query plane, we also use the explain and explain analyze on MySQL. So this select query has two conditions on the web class. Before adding any index, we need to remember that the product ID is a foreign key, so that the index on this field is automatically created by MySQL. We can compare the explain analyze between the two types of query now. So this is the query plane, only using the index created automatically by MySQL. It will have two steps. First, it will execute the index lookup, and then it will filter on the status field. With the composite index, the query plane only has one step, which is the index lookup on the order product status. It is noticeable that although the cost in the composite index is higher, but when the dataset is much larger, the composite index is expected to perform more efficiently. One thing to remember when using composite index is the leftmost prefix rules. The rule means that the index is only used when the filter starts with the first column of the index. In this case, it's the product IDs. When we only filter the status field, the index can't be used because it is not include the leftmost prefix. In this case, is the product ID column. In the third case, we demonstrate a covering index which include all the column needs by the query, the start date for the where, order ID, and status for the select statement. This allows the query to be resolved only using the covering index with access to the main table, which reduce the I/O cost and improve speed. Now let's run the explain and analyze query on MySQL. Now we'll compare the two cases of using index. The first one, we will only indexing the where clause versus the second one, we will use the covering index for both the where and select clause. We'll compare the two query plane. So you can see that the cost for the covering index is indeed lower. This is because with the regular index, MySQL still need to access to the base table to fetch the values. In contrast, all the data is already sufficient in the covering index, allowing the query to complete faster. In the fourth case, we look at the join operation between order and planes. In the first query, we lower the plane ID column so that the query cannot use any index, and the query plane has to apply the hash join, which means that the query will have to perform a full table scan to form a hash table, and then it will have to scan the entire other tables. And this is the query we can execute with the index from the plane ID, so that it will apply the next loop join strategy. So this is the illustration for the next loop join. For each row in the outer table planes, MySQL will look through the inner table order by looking for the matching rows. So in large database, next loop join combined with index will scale better and significantly improve the performance compared to the hash join. So we'll move on to the store procedure part, starting with inventory updates. This procedure allows us to update inventory with two actions, stock in and stock out. With the action is stock in, the system adds the given quantities to the current inventory. With the action is stock out, the system first checks whether the request quantity is exceed available stock. If the quantity exceeds available stock, a message error is returned, notifying that the request quantity is not sufficient. If not, stock is taken out successfully and the quantity is deducted. So now we'll test these two cases on MySQL. For the first simulation, we'll try the successful stock out. Now check the inventory before withdrawing stock. We'll have 17 units of material and 002. So now I will call the procedure to withdraw 10 units of material. Okay, so this is the result, stock out successful. And now we'll check the inventory again. So the quantity left is 7. Next, I'll run the second simulation, withdrawing stock failure due to insufficient inventory. I will call the procedure to withdraw 1000 units of stock. And the result, return an error message. Not enough stock with available only 7, while the request quantities is 1000. We also create a prop to automate the creation of production order. The procedure takes the inputs such as product ID and the required quantities. And then it's based on the bill of materials. The system calculates the total material requirements for the order and then compare them against the actual inventory. So if the material is insufficient, the prop will stop and it will return an error listing all the sorted items. If the requirements are met, the system will create a new record in the order tables here, and it will also update the inventory by deducting the used quantities. Now let's test these two cases in MySQL. In the first case, we'll create an order to produce 2 units of product P003. We'll check the current inventory and then compare with the total material required to produce 2 units of products. So this is the inventory, and this is the required quantities. So you can see that the material in inventory is enough to produce. Now I will call the procedure to create a production orders. Okay, so the result is the production order created successfully. And because the procedure updates the inventory automatically, so the inventory after will change. Next, I will test the case of insufficient material when creating 1000 units of products. I'll run the procedure. So this time, the system returned an error message, insufficient materials, and specifying the sorted amount for each material. So next, we'll move on to the fifth part, Python application development. First thing first, we'll have to connect a SQL database with Python using the MySQL connectors. What MySQL connector does, will help Pythons to run the SQL queries, get and update data, and also use the store procedures we have mentioned earlier. So from now on, we'll use MySQL connectors to complete the following tasks: the operational script, reporting modules, and user interface. In this part, operational script will run and test all the procedure we mentioned earlier on PyCharm. So now we'll briefly run through the operational script in PyCharm. First thing first, we use the update material function to call the equivalent store procedure in MySQL. The first case will withdraw 10 units of material M003. And this is the message return. For the second case, we withdraw 1000 units of material. And the message return is just similar to what we did earlier when using MySQL store procedure. The second function we use is create production order, which is similar to the store procedure we see in the earlier parts. So first, I will create the production orders for the product ID P003 with the quantity equal to 2. So this is the message return when we have enough materials. Now we'll change the quantities to 1000. Well, since we don't have enough material, this is the message return.
Now we come to the reporting module. The reporting module is designed to generate a dashboard report that helps track monthly production, monitor stock quantities by category, analyze the distribution of material unit costs, and visualize order status distribution. The first graph is monthly completed orders. This trend analysis helps production managers assess performance over time and identify months with potential inefficiencies or seasonal variation in output. The second graph is stock quantity by product category. This chart aids inventory managers in identifying which categories may be overstocked or understocked, allowing them to adjust procurement and production plans accordingly. The third one is material unit cost distribution. This box plot presents the distribution of unit costs for raw materials, helping the user monitor material cost fluctuation and detect any anomalies or exceptional high cost items. The final graph is the order status distribution. This visualization offers a quick snapshot of operational status, helping stakeholders understand production efficiency and backlog risk. Now we turn to the GUI interface that we have designed. We have already described in details about the functionality of creating and processing manufacturing orders. So we focus on other parts that I would like to mention. The first one is searching functionality. In the manufacturing of the tabs, the user only needs to type any entries and click into the search button like this. The result will be shown on the tree view. The user then clicks into the Show All button to view the original list. Next, in the raw material tab, the user can purchase material from suppliers and by typing all the entries needed and then click into the Purchase button. Yeah, here's the result. The Purchase button functions as the same as the Add button in the Supplier tab. If one of the entries is not available, the system would require the user to fill in the rest. This would help avoid no value in the database. Here is the error that the system has shown. That if the user needs to adjust the type value, so he can type the change entries and click into the Update button. Like this, I will change the material ID into M004. And here's a new result. If the user wants to delete the data, he can click into it and click Delete button.
So to conclusions, the project successfully designed and implemented a comprehensive production management system. And the system utilized MySQL as a database and Python for operational scripts and a simple user interface. Advanced database objects were developed to optimize performance and automate production workflows. Additionally, the system incorporates security roles and permissions, as well as backup, recovery, and regular data import policies to ensure stable long-term operations. For recommendation, the current dataset is still limited about 200 rows, so it is recommended to increase the volume of real data, enabling index to function more effectively and making query plans clearer on larger datasets. And consider integrating advanced features such as predictive material planning, ERP system integration and improve user interface. Okay, so this is the end of our presentation. Thank you for listening.